Hi students, welcome to the mathematics class for students of standard 12 studying in NCERT syllabus. So this is a chapter 1 part 2 video, and in this video we will be dealing with equivalence classes. Okay, let's start. What are equivalence classes? How do you define them? Equivalence classes can be defined as the subsets of elements from set A, that is set capital A, where each subset has elements that are related to a particular element, say A from A, and are also related or equivalent to each other. So how do you define an equivalence class? It can be defined as the subset. It is a subset and it contains elements from set A. Okay. Now each subset, that is each equivalence class, has elements in it that are related to a particular element, say A from A. Okay, so if you are saying equivalence class of A, the small a, so it contains elements that are related to A. Okay, and one more thing, the elements are also related or equivalent to each other. Okay, now let A be a set and R be the equivalence relation defined on it. So you are taking A as a set and R is the equivalence relation defined on it. For any element small a belonging to the set capital A, then the equivalence class of A will be a subset of A. The equivalence class of A will be a subset of A consisting of elements only from A, not outside A. Okay, and these elements, they are related to A. All those elements in the equivalence class of A will be related to A and are also related to each other. Now, equivalence class of A is denoted as this. This is how you denote an equivalence class. Okay. For instance, if B is an element in A, for example, if you take B as an element in A, and if B is related or equivalent to A, then the equivalence class of A can be written as, how do you write it? Equivalence class of A is equal to bracket B belonging to A, where A and B belong to the relation. So this is the format for writing an equivalence class. Okay. Now let's take an example. Let's set A B equals 1, 2, 3, 4, 5, and the relation defined on it is, what is the relation defined on it? That is A comma B, where A plus B is even and A and B belong to the set A. So they are defining a relation and the condition given is A plus B should be even and the elements of course should belong to set A. Now from the condition given, let's find out what are the possible pairs. Because we know the elements of set A, we can find the possible pairs. So R is equal to what? You start with 1. So 1 comma 1, of course it is going to be in the relation because 1 plus 1 is even. Then you check for 1 comma 2. If you add 1 and 2, if you take 1 to be A and B to be 2, if you add 1 plus 2, you won't get an even number. It is going to be 3 and that is odd number. So we skip that. You take 1 comma 3 then. So 1 plus 3 is 4, which is even. So 1 comma 3 satisfies the relation, so it comes inside the relation. Check for 1 comma 4, 1 plus 4 is 5, 5 is not even, so you can't take 1 comma 4. 1 comma 5, yeah, 1 plus 5 is 6, so 6 is even, so 1 comma 5 comes inside the relation. Then you go with, start with 2. Okay, so you check for 2 comma 1, 2 plus 1 is 3, 3 is not even number, so you won't take 2 comma 1. Check for 2 comma 2, 2 plus 2 is 4, which is even. So you take 2 comma 2 in the relation. Likewise, you keep checking for each and every possible pair. Okay. So 2 comma 4, 3 comma 1, 3 comma 3, 3 comma 5, 4 comma 2, 4 comma 4, 5 comma 1, 5 comma 3, and 5 comma 5. So these are the only possible pairs in the relation that satisfy the condition given. That is A plus B is even. Okay. Now, how do we go about? What are the conditions that we need to check? To prove that a relation is equivalent, we need to check for reflexive, symmetric, and transitive properties. So, if you want to prove a relation is equivalent, you have to check for reflexive, symmetric, and transitive. We learned about this already, right? So, first let's check for reflexive. For every A in A, for every small a in A comma A belongs to R. That is the condition for reflexive. That is, for every A in A comma A should belong to R. That is the condition for a relation to be reflexive. So in this case, You check for 1, that is if A is 1, then 1 comma 1 is there. 2, 2 comma 2, 3, 3 comma 3, 4, 4 comma 4, and for 5 you have 5 comma 5. So since all these identical pairs of each element of A is present in the relation, we can say this is a reflexive relation. So hence it is reflexive. Okay. The next relation that we need to check for is symmetric. So in this relation, for every A comma B belonging to R, if B comma A also belongs to R, then you can call the relation to be symmetric. That is the condition for symmetric, right? For every A comma B in the R, you have to check for B comma A. If B comma A belongs to R, then the relation is symmetric. Now this is the value of R. From the previous page, I have taken the values. Okay, so it is 1 comma 1, 1 comma 3, and so on. So looking at this relation, can you check if A comma B is an R and B comma A is also an R? So 1 comma 1, you have 1 comma 1. 1 comma 3, 3 comma 1 is there. Okay, A comma B, B comma A. 1 comma 5, you have 5 comma 1. 2 comma 2 and 2 comma 2 is the same. Okay, then 2 comma 4, you have 4 comma 2. 3 comma 1, you have 1 comma 3. 3 comma 5, 5 comma 3. 4 comma 2, 2 comma 4. 4 comma 4 and 4 comma 4 are the same. So 5 comma 1, 1 comma 5, 5 comma 3, 3 comma 5, 5 comma 5 and 5 comma 5 are the same. So we can see that for every A comma B belonging to R, B comma A also belongs to R. So this relation is going to be symmetric. Okay, that is proved. Now moving on, let's check for transitive. That is for every A comma B and B comma C belonging to R, then we have to check if A comma C belongs to R. If in case A comma C also belongs to R, then you can say the relation is transitive. You remember, right? The condition for transitive is if A comma B and B comma C belongs in the relation, then A comma C should also belong in the relation. That is the condition. Now, looking at the above relation, you can see, right, for 1 comma 1 and 1 comma 3, 1 comma 3 is there. That is A comma B and B comma C. Okay, for this we have A comma C in the relation, that is 1 comma 3 is there. Then for 1 comma 1 and 1 comma 5, you have 1 comma 5 again. For 1 comma 3 and 3 comma 1, 1 comma 3 and 3 comma 1, we have 1 comma 1 in the relation. For 1 comma 3 and 3 comma 3, we have 1 comma 3. For 1 comma 3 and 3 comma 5, we have 1 comma 5. For 2 comma 2 and 2 comma 4, we have 2 comma 4. So going like we can just keep checking for every element. Okay, we can keep checking for every possible pair. So after checking, we will find that if for every A comma B and B comma C belonging to the relation, A comma C also belongs to the relation. So what does this imply? This implies that the relation is transitive too. So because this relation has been proved to be reflexive, symmetric and transitive, we can say that this relation is an equivalence relation. Okay. Now that we have proved that the relation is equivalence, now we have proved that the relation is equivalence, we will move on to finding the equivalence classes of set A. So we have to find equivalence class of 1, equivalence class of 2, equivalence class of 3, 4 and 5. Okay. Now this is the value of R as we know. So what is going to be the equivalence class of 1? Equivalence class of 1 is nothing but a subset. This is nothing but a subset, right? It contains elements that are going to be related to 1 and also to each other. So that is the condition for equivalence class, right? So equivalence class of 1 is going to be what? Here all those elements that are related to 1, that is 1 comma 1. So here you have 1 that is related, so you pick 1 from there. Here 3 is related to 1, so you take 3. Then 5, okay, 5 you take. Again another condition is these elements should be related to each other. That is another condition, right? You can check again. So 3 comma 1 will be there, okay, 3 comma 5 will be there, 5 comma 3 will be there, 5 comma 1 will be there, 1 comma 5, 1 comma 3 and vice versa, so on. So this relation, this is a equivalence class of 1. Now what is the equivalence class of 2? Equivalence class of 2 will be those elements that are related to 2. So you have 2 here, then 4 here. So 2 comma 4 is the equivalence class of 2. Equivalence class of 3, it is going to be 1, 3 and 5. Done, right? For 4, equivalence class of 4 is going to be 2 comma 4. Equivalence class of 5, 1, 3 and 5. So now we have found equivalence classes of all elements of set A. Looking at these equivalence classes, what can you say? You can say that equivalence class of 1 is equal to equivalence class of 3 equals equivalence class of 5. So equivalence classes of 1, 3 and 5 are the same. Equivalence classes of 2 and 4 are the same. This is what we can see from what we have arrived at. Now, analyzing the equivalence classes that we have arrived at, the following conclusions can be derived. What are the conclusions? That is, we can take any element to be the representative of its class. So you take any element as a representative. You can take 1 as representative of this class. You can take 3 as the representative of this class, or you can take 5 as a representative of this class. Okay, it doesn't matter. Nothing is going to change if you take any element to be the representative of its class. Okay, then the elements in equivalence class will be related to its representative element. So each element of the class is going to be related or equivalent to the representative. Okay, na? Then the elements in an equivalence class will also be equivalent to each other. So each element of the class is going to be equivalent or related to each other. So each element will be related. That is another conclusion that we can derive. Moving on. Now we are coming across a new term, that is partitions. So what is meant by a partition? Partitions are nothing but splitting up of a set into non-empty and disjoint equivalence classes such as AI, where the union of these equivalence classes will be the whole set itself. So partition is nothing but dividing, that is splitting up. You are splitting up a whole set into non-empty and disjoint equivalence classes denoted by AI such that the union of all those classes will be the whole set, that is A itself. Now, for the above example we just did now, where set A is equal to 1, 2, 3, 5 and its equivalence classes were found out to be what? Equivalence class of 1 is equal to 135, 3 is 135, 135 equivalence classes are the same, and for equivalence classes 2 and 4 were the same. This is what we just found out, right? So, taking this as an example, we can say that equivalence class of 1 and equivalence class of 2 are partitions of set A, are partitions of the whole set A because they are disjoint sets. They are disjoint sets, which means no element of equivalence class 1 will be present in equivalence class 2 and vice versa. So, if you are going to say that this is a partition of A, okay, this equivalence class is a partition of A and this equivalence class is also a partition of A. If you are going to say these two are the partitions of A, then no element of equivalence class 1 should be in equivalence class 2 and vice versa. Okay. The union of partitions equivalence class 1 and equivalence class 2 will be equal to the whole set A itself. Now, what is the union of equivalence class 1 and 2? You can see equivalence class 1 union equivalence class 2 will be set 1, 3, 5 union set 2, 4, which is going to be 1, 2, 3, 4, 5, which is nothing but the set A itself. So, you find a union between two equivalence classes, that is two partitions. Finding union between two partitions, what you will get? You will get the whole set itself. The partitions may be 2, 3 or 4. How many numbers? Doesn't matter. So finding a union between the partitions, you will get the whole set, that is A. Okay. Now, in general, for partitions of a set A, the following conditions will satisfy. That is, no element in AI is related to any element of AJ. That is, no element in equivalence class I is going to be related to any element of, that is, equivalence class J. Equivalence class I has no relation with equivalence class J. That is, this condition will satisfy for partitions. Okay. Now, all elements in equivalence class I are related to each other. That we know, right? That is a common rule. So, for equivalence class, all elements of the subset should be related to the element, that is I in this case. And then equivalence class of I union equivalence class of J will be equal to whole set A. That we just saw, right? So if you find the union between the partitions, you will get the whole set. And equivalence class of I intersection equivalence class of J will be what? A phi, that is a null set. There is no relation between these two classes, so no element is common between the sets, so it's going to be a null set, where I is not equal to j. Got it? So these are a few conditions, a few conclusions which we derive from the above examples that we just saw. Okay. Now moving on, let's look into an example of equivalence classes and partitions so that we understand the concept even better. What are equivalence classes? What are partitions? You will understand the concept much better by going with an example. Okay. Now let's set A, B, A, comma, B, comma, C, comma, D, comma, E. That is, A is some person, B is another person, C, D, and E. They are different people. Okay. We are taking for an example 5 different people, and you can see that A and B are colored in yellow. That is because we have taken A and B such that they have the same date of birth. Okay. Now, and then C, D, and E are colored in green, which means that we have taken them to be having the same date of birth. Okay, so A and B have same date of birth, and C, D, and E have the same date of birth. Now let's set A, B, A, comma, B, comma, C, comma, D, comma, E, and the relation defined on set A is what? A, comma, B, such that A and B have the same birthday, where A, comma, B belongs to set A. So the condition that is for the relation is A and B should have the same birthday. That is the condition given. Now, what are the possible pairs that can come inside the relation? So let's see. So for A, and we know that A and B have the same birthday. So A and A, of course, will form a pair and fall in the relation, right? Then A, comma, B, B, comma, A, B, comma, B. Now we can't say A, comma, C because they have different birthdays, right? Birth date. So you can't pair any A, comma, C, A, comma, D, A, comma, E is not possible, right? So again, we have to start from C, comma, C, comma, D, C, comma, E, then D, comma, C, D, comma, D, D, comma, E, and E, comma, C, E, comma, D, and E, comma, E. These are the only possible pairs. The condition is A and B have the same birthday. So these two stand separate and these three stand separate, right? Now, to prove reflexive, looking at the relation, what can you say? For every A belonging to set A, comma A should belong to R. You have A, comma A is there, B, comma B is there, C, comma C, D, comma D, and E, comma E is there. So this proves the relation is reflexive. Okay, next, moving on. To prove symmetric, for every A, comma B belonging to the relation, B, comma A should also belonging to the relation. That is the condition for symmetric, right? Now, looking at the relation, what can you say? For every A, comma B, is B, comma A there? Of course it is. So for A, comma A, comma A is there. A, comma B, B, comma A is there. B, comma B, B, comma B, C, comma C, C, comma C, C, comma D, you have D, comma C. C, comma E, you have E, comma C. D, comma E, E, comma D. E, comma C, you have C, comma E. So for every A, comma B, B, comma C, B, comma A is there in the relation. So this relation is going to be symmetric. That's been proved. Okay. Of course, that's been proved to be symmetric. Now, the next relation that we need to check is transitive. We have to check for transitive. Now, to prove transitive, what is the condition? For every A, comma B and B, comma C belonging to the relation, A, comma C should also be there in the relation. That is the condition that is needed to be for the relation to be proved transitive. Now, looking at the relation, what can you say? Do you have A, comma B, B, comma C, and A, comma C in the relation? Of course, we have, because you see A, comma A and A, comma B, if you take, you have A, comma B again. Okay, B, comma A, and let's take say C, comma D and D, comma E. Then C, comma E, of course, is there. E, comma C, C, comma D. Then E, comma D, of course, is there. So for every A, comma B and B, comma C in the relation, you are finding that A, comma C is also in the relation. So this relation is going to be transitive also. It has been proved. Okay. Then, so because now we have proved that the relation is reflexive, symmetric, and transitive, we can say the relation is going to be an equivalence relation. It has been proved to be an equivalence relation. Now, let's find the equivalence classes for this set here. What are the equivalence classes possible? So, again, this is the value of R. Okay. Now, what are the equivalence classes possible? We can say equivalence class of element A. So we know that a set A has 5 elements. So equivalence class of A is going to be what? A and B. That's it. It won't be related to any other element other than B and A itself. Okay. Then equivalence class of B is going to be again A comma B only. Equivalence class of C is going to be C, D and E. From the relation you can say it is C, D and E. And then for equivalence class of D is going to be again C, D and E. Equivalence class of E is also going to be again C, D and E. So what is the finding here? Equivalence class of A is equal to equivalence class of B. Then equivalence class of C is equal to equivalence class of D is equal to equivalence class of E. So what you can say? You can say that equivalence class of A and equivalence class of C are the partitions of set A, which means no element in equivalence class of A is present in equivalence class of C. And it also means that the union of these two partitions will result in the whole set, that is A itself. That is A comma B union C comma D comma E will be A B C D E. And then the intersection of A comma equivalence class of A and equivalence class of C will give you a null set, that is 5. So there is not going to be any common element between these two sets. So looking at this, we can say all these conclusions, right? So no element of A is related to element of C. That's what we just found out. Then equivalence class of A union equivalence class of C is equal to the whole set A, and the intersection will give you a null set. So these are the findings from this equivalence classes. So with this, I think we have come to the end of this video. I hope you guys got a very clear picture about what are equivalence classes and what are partitions. Okay. So in the next video, we'll be starting with exercise 1.1 sums. So we will, I think we have some around some 16 sums problems in the exercise 1.1. We will be doing each sum in detail, one by one. Okay. I'm sure the next video is going to be very fantastic. Thank you.